All right, let's get right into it. We're going to pull back the curtain on something you use every single day, whether you know it or not: how machines learn to make predictions. It can feel like some kind of digital magic, but today, we're going to break down exactly how it all works. I mean, really think about it. You get an email from a supposed prince who needs your help with his fortune, and poof, it's already in your junk folder. How? How did your inbox know to do that? Well, a lot of the time, the secret isn't magic at all. It's actually a surprisingly simple and powerful algorithm, just playing the odds.
Because that's the real secret sauce here. These systems aren't trying to understand language like a person does. Not at all. The whole thing is basically just making a very, very educated guess, all based on patterns and probabilities it's learned from millions of emails it's already seen. So, to see how these guesses are weighed, let's start with one of the most intuitive models out there, the decision tree. The best way to think of it is like a super smart flowchart that takes a whole mess of data and turns it into clear, simple answers. Okay, so put yourself in the shoes of a marketing manager for a second. Your big goal is to figure out who's most likely to buy a new computer. And you've got this giant spreadsheet of data: age, income, credit rating, all of it. It's just a wall of information. It's almost impossible to see any real pattern just by looking at it. And that's the million-dollar question, right? How can a machine look at this flat, chaotic table of data and somehow pull out a perfect little flowchart that can predict what people will do? What is the actual method? Well, the answer has this fancy name, recursive partitioning. But trust me, the idea is incredibly simple. The algorithm just splits the data over and over again. It starts by picking a feature, like age. Then it figures out the best way to split everyone into age groups. It measures how much clearer the picture gets, and then it just does that all over again for each new group it created. It's a loop. So how does the algorithm know which split is the best one? Well, its entire goal is to create what we call purity. A group is considered perfectly pure if every single person in it has the exact same outcome. So a group where all 5 customers bought a computer, that's a pure group. The algorithm is constantly on the hunt for questions that lead to these perfectly pure little buckets. And check this out, this is where the magic happens. After the algorithm just asks one simple question about age, a clear pattern immediately pops out. We discover a group, the folks between 31 and 40, where 100% of them bought a computer. That's a perfectly pure node. The algorithm loves this. It's a dead end, a final answer. For that group, we don't need to ask any more questions. Okay, but this whole process of just asking more and more and more questions, well, that leads us right into the single biggest challenge in all of predictive modeling. How do you build a model that's not too simple, not too complex, but, you know, just right? And yep, this is what we call the Goldilocks problem. On one side, you've got underfitting. The model is so simple, it totally misses the real patterns. But on the other side, you have the main villain of our story today: overfitting, where the model gets way, way too complex. So, what is overfitting? It's what happens when a model gets so obsessed with the data it's training on that it starts to memorize every little random detail and fluke. It's kind of like a student who memorizes the answers to the practice test perfectly, but then completely bombs the final exam because they never actually learned how to solve the problems. So how do we stop this from happening? Well, we have a kind of control panel with a bunch of levers we can pull. We can tell the tree, hey, don't grow any deeper than this. Or we can set a rule that it can't make a final decision based on just a handful of people. We can even tell it to just stop splitting once a group is, say, 95% pure. That's good enough. These are the tools we use to keep the model from getting out of control. Okay, let's totally switch gears now and look at a completely different way of doing things. We're going to look at an algorithm that some people have nicknamed the idiot's classifier. And yeah, that sounds pretty harsh, but as you're about to see, its simplicity is actually what makes it so brilliant. And here's why it gets that naive name. It's built on this one huge and, let's be real, almost always wrong assumption that every single word in an email is totally independent of every other word. The model doesn't see sentences or grammar, it just sees a jumbled bag of words. To this model, the phrases dear friend and friend dear mean the exact same thing. Now, this super simple approach actually works surprisingly well most of the time, but it has one giant glaring Achilles heel. What on earth is supposed to happen when it comes across a word in a new email that it has never, ever seen before in that category? Let's make this super clear. Imagine a new email comes in that says lunch money, money, money. But in all of the data we've trained our model on, the word lunch has only ever shown up in normal, legitimate emails. It has never once appeared in a spam message. So, what's the probability of seeing the word lunch in spam? Well, based on our data, it's 0. A big fat 0. And that is a catastrophic problem. See, we're multiplying all these probabilities together to get our final spam score. So what happens when you multiply times anything by 0? The entire calculation becomes 0. It doesn't matter that the word money is a huge red flag for spam. That one single word lunch just torpedoed the whole thing. The model completely breaks. Luckily, there's this really clever little trick called Laplace smoothing. And the idea is just beautiful in its simplicity. We just pretend we've seen every single word one more time than we actually have. We just add a count of 1 to every word in our dictionary. And just like that, the word lunch no longer has a probability of 0. Boom, problem solved. Our model is now much more robust. So we've now seen 2 totally different ways to make predictions: the methodical decision tree and the brilliantly simple naive Bayes. And by looking at them side by side, it really shines a light on the single biggest choice a data scientist has to make. This isn't just about picking an algorithm. It's about a fundamental tension: the choice between a model that predicts with perfect accuracy and a model that you can actually understand. And this table just lays it all out perfectly, even within the same family of models. On one side, you've got CART, which is like a sculptor. Its only goal is raw predictive power. It grows this huge, complex tree with thousands of simple yes or no questions, and then it carefully chisels it down to its most powerful form. It's a black box powerhouse, perfect for things like fraud detection, where you just need the most accurate answer possible, no questions asked. But then you've got Chade, who's more like a cautious gardener. It only adds a new branch if it's statistically significant and actually useful. This gives you a wider, simpler tree that's super easy to explain. Marketers love it because it helps them understand why their customers are behaving a certain way. And this quote just hits the nail on the head. The question you always have to ask is, what is my number one goal here? Do I need a flawless but maybe unexplainable prediction for my credit risk model, or do I need a crystal clear explanation for my marketing team, even if it's a tiny bit less precise? The goal always dictates the tool you choose. It's never about finding the single best model, but the right model for that specific job. Which leads us to one final really interesting thought to leave you with. We know for a fact that the entire naive Bayes classifier is built on an assumption that is just plain wrong. Words are not independent. And yet, the algorithm works incredibly well. So it really makes you wonder, right? If a model that's this naive can solve problems so effectively, maybe some of the really complex challenges we face are actually, at their core, a lot simpler than we give them credit for. It's something to think about, isn't it?